Myself, Dr. Anand Tirtha B. Gudi, Professor and Coordinator, PG Studies, Department of Electronics and Communication Engineering, Global Academy of Technology, Bangalore 98. Today's session is about digital electronics. In this, we are going to cover converting hexadecimal to decimal topic, and under the octal numbers, in specific, we are going to cover binary to octal conversion, finding the base value for a given number, and then we are going to cover complement of binary numbers. Under that, binary subtraction using ones complement method, and also we are executing the binary subtraction using twos complement method, converting given decimal number into binary, octal and hexadecimal number is given as an example at the end of the session. First, let us start with hexadecimal to decimal conversion. Count the number of hexadecimal digits before the radix point and put the weight of each digit as 0, 1, 2 from right hand side to left hand side. Let n is the total number of bits or digits. The last digit has a weight of n minus 1. Second step to be followed is count the number of decimal digit after the radix or binary point and put the weight each digit as minus 1, minus 2, minus 3 from left hand side to right hand side. Let m is the number of bits. Last bit or digit has weight equal to 2 to the power minus 1. The last step is supposed to be followed is use the generalized equation for converting it to decimal equivalent. Finally, add all the product terms which gives the number equivalent to decimal number system. Let us take an example how to convert the given decimal number, hexadecimal number into a decimal system. The given number in hexadecimal is ABC point CD base 16, and it should be converted into decimal number. According to the procedure explained already, take the numbers ABC dot CD as like shown, then C must be multiplied by 16 to the power 0, and next B must be multiplied by 6 to the power 1, and A, that is MSB, must be multiplied by highest value, that is 16 to the power 2. And after the radix point, the C is there, the C is multiplied by 16 minus 1, and D must be multiplied by 16 to the power minus 2. Then go on multiplying. What is the A? A is equal to 10 and B is equal to 11 in decimal, and C in hexadecimal is 12 in decimal number, and similarly after the decimal point, C is considered as 12 in decimal and D is considered as 13 in decimal. Now the product value 10 into 16 to the power 2 is equal to 2560, and 11 into 16 to the power minus 1 is equal to 176, and 12 into 16 to the power 0 is equal to 12. Similarly, after the decimal point, 12 into 16 to the power minus 1 is equal to 0.75, and 13 into 16 to the power minus 2 is equal to 0.050. Now the left side, whatever the product values are there, that you should have to sum it. So that gives, we are going to write the sum value as 2748, and after the decimal point, 0.75 plus 0.050 is going to give 0.80. Hence the result of the hexadecimal number ABC point CD is equal to 2748.80 in decimal. Next topic, binary to octal conversion. Here also we are going to follow certain procedural steps. Where is first step? Group the given binary digit or bits from RHS to LHS as before binary or radix point. Later 3 bits we should have to segregate at a time. If the last group is not equal to 3 bits, prefix the required number of zeros. After adding the number of zeros at the extreme MSB, then the value is not altered and the value will not going to change. Write the corresponding octal number for each group gives the octal representation of the binary digits. The next step, group the given digit or bit from LHS to RHS after of radix point required number of zeros and the value will not change. The last step, write the corresponding octal equivalent number for each group gives the octal representation of binary digits. By following these procedural steps, let us take an example and solve. Example, the given value in binary number is 1 0 1 1 1 1 1 0 1 1 before the radix point. After the radix point 1 0 1 1 1, then you should have to arrange as like shown. Now after the decimal point an arrow mark is marked towards the right side and before the radix point the arrow mark is marked in towards the left. Now as per the step number 2, we should have to divide the number of binary numbers from right to left in 3. So 1 2 3, just we are going to put a comma and next 1 2 3 bits 1 comma, after that 1 1 0 and we are going to put a comma, lastly only 1 we are going to get here, but to make it 3 numbers we are going to add 2 zeros. By adding these 2 zeros or prefix, value of the given number is not going to change. Similarly, when it comes to after the radix point 1 0 1, we are going to mark a dot or comma, after that only 1 1 is there. To satisfy the number of digits equal to 3, then we are going to add 1 0 at the LSB or extreme right. So by adding this 0, the value is not going to change. Then we are going to evaluate the value 0 1 1 as equal to 3, because it is first one is a LSB of 0 1 1 is equal to 2 to the power 0 into 1 and 2 to the power 1 into 1 and 0. If you are going to add, the sum value is going to be equal to 3. Similarly 1 1 1 value we can decode it as 7 and 0 1 1 we can code it as 3 and 0 0 1 we can make it as 1. So after the radix point 1 0 1 can be converted into a decimal value, that is 2 to the power 0 into 1 plus 2 to the power 1 into 0 plus 2 to the power 2 into 1, then automatically 2 to the power 2 is 4 plus 1, that is 5. Similarly 1 1 0 can be coded as 6. Therefore the binary value what we have given is before the radix point is going to get the value 1373 and after the radix point 56. Then the binary equivalent we are going to write it as 1373.50 in octal. Next, hints for conversion is very important. From other to decimal, if we want to convert, then the values must be multiplied. For example, if your intention is to convert the binary number into decimal number, then the given binary number must be multiplied by 2. For example, if we are going to say 110 is there, so given number of binary, if we want to convert it into a decimal number, then how we should have to do is, this is 2 to the power 0, this is 2 to the power 1 and this is 2 to the power 2. Therefore what we are going to do is 1 into 2 to the power 2 plus 1 into 2 to the power 1 plus 0 into 2 to the power 0 is equal to how much value in decimal. Then this is 4 plus this is 2 to the power 1 is 2 into 1 is 2 plus 2 to the power 0 is 1. Of course 1 is there, 0 is there, hence this is equal to 0. Hence the value is equal to 4 plus 2, that is equal to 6 in decimal. Similarly, what we are going to say, whenever the number is given, okay, and if you want to convert that number into a decimal value, then we should have to multiply. That is the meaning. and decimal to other we should have to divide. For example, if we are going to consider the number 30 which is given in decimal, now if you want to convert it into binary, then what we are going to do, simply we are going to divide. So that is 15 times it will go and the remainder value will 0, and once again it will divide by 7 and the remainder is going to become 1, and once again we are going to get a value 3 and the remainder is 1, and after that finally when you are going to divide 3 by 2, it is going to give a result once value quotient value 1 and remainder value is equal to 0. Then we are going to write the binary value like 1 1 1 1 0 binary base 2 for the given number 30 in decimal. So like that, given value if it is in decimal and to convert into the other base value, then with the base value the given number decimal must be divided. So that we are going to show, and after that the last number is binary to hexadecimal. Then what we are going to do, we are going to make a 4 number of groups from before the radix point from right to left, and after the decimal point from left to right, and we are going to segregate into 4. After that we are going to convert it into the equivalent of hexadecimal number. So similarly, binary to octal, instead of making 4 number groups, we are going to make it only 3 number groups, and then the octal number is going to be formulated. And hexadecimal to octal, if is the question, then automatically what we are going to do is, first the hexadecimal number is converted into binary, and from after that the binary to octal conversion procedure must be followed to convert the given decimal number into octal. Sometimes we come across with a large binary number that has to be converted into decimal number. For that what we do is, usually first we are going to convert the given binary number into hexadecimal number, then after that we are going to convert the hexadecimal number into decimal number. Now we are going to take an example, that is determine the base value of x if the given value 211 with the base x value that is unknown is equal to 152 in octal. So under this situation what we are going to do, just we can solve on the board. So 211 is the given value with base x, and 152 with the octal value. So this octal value, if you are going to decode it, then automatically 1 into 8 to the power, this is 8 to the power 0, this is 8 to the power 1, this is 8 to the power 2. So therefore 1 into 8 to the power 2 plus 5 into 8 to the power 1 plus 2 into 8 to the power 0. So then that is 8 into 8 is just if you are going to sum these values, then we may get this is equal to 106. Then finally this if you are going to decode it, this is x to the power 0, this is x to the power 1, this is x to the power 2. So then we can write it like this: 2 into x to the power 2 plus x into 1 or 1 into x, and finally this is x to the power 0 is equal to 1, and that is multiplied by 1 is 1. So therefore we can write 2x square plus x plus 1 is equal to 106. Then 2x square plus x minus 105 we can is equal to 0. We can say like this, it is equal to 0. Then if you are going to separate or if you are going to factorize this, then x minus 7 into we are going to get 2x plus 15. Then x value may become equal to 7, or x value may become 15 divided by 2, that is equal to minus 15, that is minus 7.5. This is invalid number, hence we may be considering the x value is equal to 7. With that base, what we can write is 211 base value 7 may be equal to 152 base value as 8. Once again we will go with one more example to familiarize with this kind of examples. determine the base value of x. The given value is 193, base value x is equal to 623 with base 8. Now similar steps what we followed we are going to follow, then we are going to write x square plus 9x plus 3 is equal to 8 square into 6 plus 8 to the power 1 into 2 plus 8 to the power 0 into 3. Then the value we can write it as x square plus 9x plus 3 is equal to 403. Then the equation 403, if you are going to take it left LHS, then automatically this becomes x square plus 9x minus 400 is equal to 0. Then we can factorize it like x minus 16 into x plus 25 is equal to 0. Then x plus 16, x is equal to 16 or x is equal to minus 25. So x minus 25 is an invalid value, hence we are going to take x value is equal to 16. Then we can write it as 193 base 16 or hexa base is equal to 623 base 8. Next, different number system chart. In this, whatever so far we have discussed in digital electronics fundamentals, we are going to see in one single chart. First column explains the decimal number system, and this is binary system, and this is the octal, and last one is the hexadecimal number. So the binary number here we are using 4 bits for representing, because minimum 4 bits are required to represent an hexadecimal value till from 0 to at least 15. So therefore what we are going to write is all binary values are 0 0 0, means that it is indirectly we are going to call this as 8421 code. So according to that, the decimal value in binary, decimal value 0 in binary we are going to write 0 0 0 0, and octal value is also becomes 0, and hexadecimal value is also looks like 0. This is okay, looks to be better up to the value 7. So up to 7, whatever it is there in the decimal 7, it is same as in octal value also, it is same as okay in hexadecimal also. Now one 8 decimal number, if you are going to write in binary, that is going to take 1000. Then we may be writing the octal equivalent of decimal number 8 as 10. Why? This is our question. Now if I am going to write 1000 of a binary number is equal to what value in octal, then according to our procedure we should have to mark, okay, this is 0 0 0. Now the radix point is not available, then I should have to make it as 3 numbers group from right side to left. Here I should have to add 2 zeros. So then automatically this value becomes 0 in octal, and this value becomes 1 in octal. Then the equivalent value 1000 in binary can be rewritten as 10 in octal. Therefore the value of 8 in decimal system can be rewritten as 10 when it comes to octal, and in hexadecimal it is retained as it is. Similarly, if you are coming down, then automatically the numbers similarly we are going to decode up to 17, and what is the difference in this we are observing is the 12 value, the base, this decimal value 10 is written as equivalent to 12 in octal, same thing is coded as A in hexadecimal system. So therefore 10 onwards up to 15 it is coded as in hexadecimal A B C. 10 is equal to A, 11 is equal to B, and C of decimal number hexadecimal is 12 in decimal, and 13 in decimal is D, and 14 in decimal E, and lastly the value 15 in decimal is written as F in hexadecimal system. So this complete chart is giving us a complete idea about the discussed number systems. Next topic is complement of a binary number. First we are going to take ones complement. Ones complement of a binary number is just an inversion of the individual bits. For example, if we are going to take one example just to find the complement, then y can be given as 1 1 1 1 0 1 0 0 1 0 0 1 1. So if you are taking the y complement, then just it is a inversion. So this first one can be rewritten as 0, second one is written as 0, third one is also written as 0, fourth one is also written as 0, the next coming 0 can be written as 1, and this one can be written as 0, 1, 1, and 0, 1, 1, 0, 0. That is indicated as a complement of the given number y. So that complement can be rewritten as the y bar, also it can be rewritten as y dash. Similarly, the 2's complement of a given number can be found by adding 1 to the least significant bit of the 1's complement number, and then the example what we can depict here is the given number y is equal to 1 0 1 0 0 1 0 0 1 0 0 1. So that number is taken as it is here, and then we are going to find the 1's complement of the given number. So this 0 as written 1 as written as 0, here the given value 0 as written as 1, and after that we are okay, this 1 is 0 and 0 is 1, like this. Okay, all individual values are inverted and it is written like this. After that we are going to add 1 to the extreme LSB, we are going to add 1 to convert it into 2's complement. In this case 0 plus 1 is 1, and 1 as it is we are going to take here, and 0 plus 1, this is 1 as it is, since the 2's complement value of the given number becomes 0 1 0 1 1 0 1 1 0 1 1 1. 2's complement method is used to represent negative numbers. Whenever it is a negative number representation is required, at that time we will go with the 2's complement method of converting the binary numbers into decimal value or any other. So now if complements of binary numbers are used in digital computers to make logical manipulations and subtraction operation easy. These are the two major advantages of a 2's complement method. Now, binary subtraction using 1's complement method. Consider two binary numbers m and n. If y is equal to m minus n, then m is treated as minuend and n is treated as subtrahend. Now, the procedure: first 1's complement of the subtrahend can be taken, after that add the 1's complement of subtrahend to the minuend. In this case, in this particular operation we may come across case 1 and case 2. In case 1, if after the addition 1's complement, when we are going to add with 1's complement of the subtrahend, if we are going to add with the minuend, if the carry is generated, that carry we are going to call end around carry. As a result of this addition process, then this addition process may not be able to give the correct required result. Even though you are adding the minuend with the 1's complement subtrahend value, then if carry is generated, then we are not going to consider that as actual result. To get the actual result or the true result, carry generated must be added to the LSB of the remaining part of the result obtained. Such example we are going to see now. Example 1, find y is equal to m minus n if the m value is 1101 with base 2 and n value is equal to 1000 with base value 2. Here the m is just for our convenient and to check or cross verify whether finally the result what we are going to obtain are correct or not. Just we have given m value 1101 binary can be rewritten as 13 base 10, and also n can be rewritten as 8 base 10. So in decimal, if we are going to conduct the operation, or if you are going to carry out the operation of n minus n, then it is 13 minus 8 is equal to plus 5 may be the result. Now, so the same thing whether we are going to get with our binary operation or not, let us see. M is treated as minuend and n is treated as subtrahend, and take 1's complement of the subtrahend. So 1's complement of n is equal to 0, 1, 1, 1, and given menu end is 1, 1, 0, 1, and that is going to be added with 1's complement value of n, that is 0, 1, 1, 1. Then automatically 1 plus 1 is equal to 1, 0, that 0 is written here, 1 is carry. So that 0, 1 plus 1, that is equal to once again 1, 0, then 1 carry is taken here. 1 plus that carry, we are going to get 1, 1, that 1 is taken here and 1 is written here. So 1 plus 1 is equal to 0, and automatically 1 is taken as carry. So once this carry is going to be generated, along with the carry, if you are going to read this as a result, it is not the true value. Hence in this case, what we said, when the carry is generated, automatically that carry must be taken to the LSB for addition. If you are going to add this carry to LSB, then our result is 1, and this becomes 0, as it is there is no value, and this is becomes 1, and the last 0 is transferred here. Then we are going to add the positive sign with this, and we are going to read the result as plus 0, 1, 0, 1, that 0, 1, 0, 1 is equivalent of plus 5 in decimal, and plus value is, if you are going to add whatever we have seen here in decimal subtraction, the positive value we are going to get at the result of value 5, the similar value we are going to get here. So to get the actual result, that is the conclusion, to get the actual result or the true value, the carry generated must be added to the LSB of the remaining result part when you are doing the subtraction operation with 1's complement method. And in the same 1's complement method, another case we can deal like this. If carry is not generated, when we are going to add two values, like one is menu end, another one is 1's complement of subtrahend, if the carry is not generated as a result of this additional process, then this is addition process may not able to give the correct required result. To get the actual result or the true value, we should take the complement value of the result obtained with a negative sign. To do the complete operation or full understanding of the case 2, we are going to give one more example here. The find y is equal to n minus m. Same value we are going to take for m in the previous case, the 1101 base 2, and n value may be 1000. Here m value can be coded with decimal number 13 and n value as 8. Now only the difference is y is equal to, instead of m minus n, here it is reverse. It is y is n minus m, that is 8 minus 13 must be equal to minus 5. So n is considered as menu end and m is considered as subtrahend. Take 1's complement of subtrahend, and that 1's complement of subtrahend can be written as m is equal to m of the complement value is equal to 0, 0, 1, 0. Then given menu end value 1, 0, 0, 0 may be added with the 1's complement m. So that is 1, 0, 0, 1, 0. So then 0 plus 0 is 0, 0 plus 1 is 1, and 0, 0, 0 plus 0 is 0, 1 is as it is, we have taken 1. And here we have not observed any carry. When the carry is not generated, we should have to take the 1's complement of this result, 1's complement of this result with a negative sign. That 1's complement of this result is nothing but here 1 is there, that 1 is treated as 0, and the second MSB value is 0 is 1, and this 1 is written as 0, and lastly this 0 is written as 1. And when the carry is not generated, already we have said it should be read as minus, and the remaining part of the result must be taken, this result part is considered with 1's complement. So therefore the result is minus 0, 1, 0, 1 base 2. That value of 0, 1, 0, 1 base 2 is treated as decimal equivalent 5, and minus value is taken here. Therefore whatever we have seen here, the value should come as minus 5, that is achieved here. Next, binary subtraction using 2's complement method. Consider two binary numbers m and n. If y is equal to m minus n, here m is considered as menu end and n is considered as subtrahend. First, the procedure. The procedure is 2's complement of subtrahend can be taken and add 2's complement of subtrahend to menu end. once again after doing this, okay, we may come across two cases. The first case, if the carry is generated because of the additional process, if the carry is generated as a result of this additional process, it is discarded and the remaining part of the value of the result is giving the true value what we are expecting. For that we are going to solve one example. So find y is equal to m minus n. The same m is equal to 1 0 0 1 and n is equal to 0 1 0 0. So equivalent value of m in binary and decimal are given here. So it is equal to 9. N value which is given in the binary can be read as 4 in decimal. So then if we are going to conduct the operation or y is equal to m minus n, in decimal it is 9 minus 4, the result is plus 5. The m is taken as minuend and n is taken as subtrahend, say, and take 2's complement value of subtrahend, then 1's complement of subtrahend n is written as 1 0 1 1 and 1 must be added to LSB of that number. So to make it as 2's complement of n, so that is shown here. 1 plus 1 is 0, the carry 1 is taken here. Once again 1 plus carry value 1 is 1 0, then 0 is written here. Once again 1 is taken here, so 0 plus that carry 1 is 1, and then 1 plus that is as it is 1 is taken here. So 2's complement of n is equal to 1 1 0 1. Given menu end is 1 0 0 1, and for that we should have to add 2's complement of n, what is there here, just we are transferring here. So then 1 plus 0 is 1 and 0 plus 0 is 0, then 0 plus 1 is 1 and 1 plus 1 is 1 0, then 0 is written here and 1 is shown it as carry. So in this addition the carry is generated. To read as actual result, what you supposed to do according to the procedure is the carry what we are going to see here is discarded. In place of that carry we are going to add the positive sign, and after discarding the 1 and adding the positive sign, what the result, okay, we are going to write is plus 0 1 0 1 is written here. Plus 0 1 0 1 with base 2 is nothing but the plus 5 in decimal. Whatever we have already shown at the top, okay, that is 9 minus 4 is equal to 5, that we have already opened. Just for verification we may be doing this particular decimal operation and it has come true. The second case in 2's complement, if after the addition of menu end and 2's complement of subtrahend, if the carry is not generated as a result, then this additional process may not be able to give the correct required result. To get the true value of the result, we should take the 2's complement of the result obtained with a negative sign. Example, y is equal to n minus 1. Just the same value of m in the previous case what we have taken, the same value is taken here, 1 0 0 1 base 2 and n value as 0 1 0 0 base 2. So m value can be read as 9 in decimal and n value in binary is read as 4 in decimal. Now the decimal operation y is equal to n minus 1 is written as 4 minus 9, that is going to give the result minus 5. Okay, now after completion of binary subtraction using 2's complement, we is supposed to get minus 5. So then what we should have to do is we should have to consider take the subtrahend value, okay, that subtrahend 2's complement value we should have to consider. Yes, it is a menu and add 2's complement of m. So then we are going to get the carry is not generated. If the carry is not generated, then what we should have to do, the 2's complement of the result, so that is 0 1 0 0, that must be added by 1, and then this 0 1 0 1 is taken with a negative sign. Hence the result is minus 0 1 0 1 base 2 is equal to minus 5 base 10. Perform the subtraction using 1's complement method. Few more examples we are going to take. Find y is equal to n minus n if m is equal to 111.10 base 2. So in the previous cases we were seeing the before the radix point numbers were there. Now decimal or fractional values are also given in this. So n is taken as 101.01. In such cases, how to carry out the performance of 1's complement subtraction and 2's complement subtraction. So now the m value is taken here, and the m value may be this. It is equal to 7.5, and n value equivalent of decimal is 5.25, and if you are going to make the simple operation in decimal, 7.5 minus 5.25 is going to give the plus value 2.25. Then here m is considered as a minuend and s is considered subtrahend. So take 1's complement of subtrahend, that n subtrahend 1's complement value can be inversion, that is 010.10. We can convert like this, and given minuend value, that is 111.10, must be added with the 1's complement of n. So that is 0 is 0 plus 0 is 0, 1 plus 1 is 10, 0 is taken here and 1 carry is added with this one. So 1 plus 1 is 0. Once again the carry is there, 1 plus 1 plus 1 carry, that is 1, and here it is carry is shifted here, 1 plus that carry value 1 is going to give the result 0, and that final 1 is taken as a carry. Then this carry must be added to the LSB. So then if we are going to see the result here, that is 010.01. So this is going to be the result, and that along with the positive sign 010.01 base 2 is equal to plus 2.25, because 01 is giving the value. This is 2 to the power minus 2, and this is 0 into 2 to the power minus 1. 0 into 2 to the power minus 1 becomes 0. So 1 into 2 to the power minus 2 becomes 1 divided by 2 to the power 2, that is 1 divided by 4. That is going to give the result of fractional value 0.25, and 010 is nothing but 0 into 2 to the power 0, and 1 into 2 to the power 1, and 0 into 2 to the power 2. In this part of the binary number, the value 2 we may be getting as a decimal equivalent, and the fractional value 01 binary we are going to get 0.25 with the positive sign. Whatever we have done here with the decimal number, it has come true. So to get a true value of result, carry generated must be added to the LSB of the remaining result part when we are going to do the 1's complement operation of subtraction with this fractional values. Similarly, the example B, that find y is equal to n minus 1 if m is equal to 111.10 base 2 and n value is equal to 101.01 base 2. So here once again the decimal operation is carried out for our satisfaction, and it is m minus n, then 7.5 minus 2.25 is equal to plus 2.25. But here the take 1's complement of the subtrahend, and the subtrahend value is m here now 0 0 0, because 111 is there, that subtrahend value if you are going to complement, then it is 0 0 0 and 0 1. That value if you are going to add with minuend value of n, then automatically 101.01 and added with 000.01. The result is the 1 additional value gives 10, the 1 is taken carry, and this is written as 0, that carry the 0 plus that carry value 1 is becomes 1, and there is no 1 plus 0 is 1, and 0 plus 0 is 0, and 1 plus 0 is 1. So the obtained result is 101.10. Carry is not generated. Hence the result, one's complement of obtained result with a negative sign, that already we have seen in the procedure. Therefore the obtained result complement value means 0 is treated as 1, and this 1 is treated as 0, and this 1 as written as 0, this middle 0 as written as 1, and this extreme MSB is treated as 1 as 0 with a negative sign. So that 0 1 0 portion of the binary value is exactly equal to 2 in decimal, 0.01 fractional value in binary is exactly equal to 0.25, and this negative sign if you are going to add whatever we are decoding, minus 010.01 base 2 is equal to minus 2.25 base 10. So then our conclusion is one's complement of obtained result with negative sign will be the true value of the result. Now similarly we are going to perform the subtraction using 2's complement method. Here also we are going to consider the fractional part, because it was not considered in the very first example of 2's complement subtraction. So now the y is taken as m minus n, and if m value is equal to 11.10 and n value is 101.01 in binary, then m and n are well defined. Equivalent value of m in decimal is 7.5 and n is 5.25. The decimal number in decimal, if you are going to evaluate the value of subtraction, that is y is equal to m minus n, then 7.5 minus 5.25 is considered as the value plus 2.25. Then m is the menu end and n is the subtrahend. Take 2's complement of the subtrahend. So that subtrahend 1's complement must be carried out first. The n is taken as subtrahend, therefore the n 1's complement must be taken 0 1 0. Instead of 1 0 1, it is written as 0 1 0. Point instead of 0 1, we are writing as a complement value 1 0. Then we should have to add 1 to the LSB. Then the final value 2's complement of n becomes 0 plus 1 is 1 and 1 as it is, then 0 is taken and 1, there is no addition, and 0. So therefore this 2's complement of value n must be added with the menu end. The given menu end value is equal to 111.10 and add 2's complement of n, that is 010.11, obtained the result, that is 0 plus 1 is 1 and 1 plus 1 is 0, carry is going to be added here, that 1 plus carry 1 is equal to 1 0, then 1 carry is taken here, 1 plus that carry is equal to 1, and then 1 plus 0 plus the carry what we are taking from backside is 1, then automatically 1 plus 1 becomes 1 0, that 0 is taken here and 1 carry as it is going to remain. So the carry is generated, then the carry is going to be discarded and the remaining part of the result is read as the true value of the result. Once the carry is discarded, there we should have to add a positive sign. Hence the result obtained can be rewritten as there, where is the carry is there, no, that carry is discarded and replaced as a plus, and remaining part is written 010.01. That binary equivalent can be rewritten as plus 2.25 base 10, that is already verified. The last example, if we are going to interchange, that is nothing but the highest value must be taken as subtrahend and the least value given must be taken as menu end, then we are supposed to get a negative value. So here in this example 2's complement method of subtraction with minus or the subtracting the higher value in the lower value we are doing. So therefore here the find y is equal to n minus m. If m is equal to 111.10 and n is 101.01, m value is 7.5 and n value is 5.25. In decimal, y is equal to n minus 1 and 5.25 minus 7.5, then automatically the value of the result is with a negative sign 2.25. So take the 2's complement of subtrahend. So first we should have to carry out 1's complement of the subtrahend, that is m, that m is 111.10, then it is written as 000.01 and with its 1's complement, then 1 must be added to its extreme LSB, then 2's complement of n can be rewritten as 000.10. So given menu end value is 101 n, that is 101.01, then 2's complement value of m must be added with that, that is going to end up with the result of 1 plus 0 is 1 and 0 plus 1 is 1, 1 plus 0 is 1 and 0 plus 0 is 0 and 1 plus 0 is 1. Obtained result, here the carry is not generated. If the carry is not generated, then 2's complement of obtained result with a negative sign will be the true value of the result. Therefore 1's complement of the obtained result must be taken first, that is 010.00, then 1 must be added to the extreme left to convert it into 2's complement. So 2's complement of the obtained result is equal to 010.01 with negative sign. So hence the result finally what we can write is minus 010.01 base 2 must be equal to, as it is minus sign, with the remaining part 010 can be written as 2 in binary is decimal, and binary equivalent of 0.01 may be written as 0.25. So total binary value can be represented as the minus 2.25 with base 10. So now the final one example what we can take is, once we are able to solve this example, we conclude like this: we have got something out of this session. So let me do this example on the board. The given number is 57.625 with the base value 10, and now we are interested in different values of base. Okay, that is, the first one is what is the value of this decimal number with the binary, and what value you are going to quote it for the octal, and the last one is the hexadecimal. Now once our this we are seeing, then 57 must be divided by 2 in order to convert it into a binary. So then automatically this is 56. The 56 can be 50, 25 means 50, and 22, that is 27 into 2 is 14, and then 2 plus 1 5, that is 54, and now it is 28. So now 28, this is the one is 1, and then 2 this will go, that is 14, and the remainder is equal to 0. Or next is 2, it will go by 7, the remainder is equal to 0. Next 2, that is just 2 into 3 is 6, 3 times, and the remainder is 1. After that 2 will go 1 time, and the remainder is 1. So therefore from here to here, if you are going to write 1 1 1 0 0 1, whether this is equivalent of binary is equivalent to 57 of decimal. Whether it is correct or not, let us see. This is 2 to the power 0, this is 2 to the power 1, this is 2 to the power 2, this is 2 to the power 3, 2 to the power 4, and 2 to the power 5. So this value is 1, this is 2, 4, 8, 16, and this is 32. So this becomes 32 plus this is 16 plus this is 8, this plus 1. So 32 plus 10, 42, plus this is 48, plus 48 plus 8 is 56, 56 plus 1 is 57. So the binary number 111001 of binary is equivalent to 57 of decimal. So this is very important for us now. So then what we can do, we can take this 0.625, then we should have to multiply by 2. This is going to give 1.250. So then the carry is generated 1.250, the carry is generated, hence we are going to take this as 1. After that only 0.250 we are going to multiply with 2, that is going to give a result of 0.500. So the carry is not generated. Then once again we are going to take this into multiplied by 2, then it is going to give the result like this. So then we are going to take this carry from top to bottom, we are going to write. So then the equivalent value 0.625 in decimal is equivalent to 101 in binary, that is with the decimal value. Here we should have to show 0.101 with the base value is equal to 0. Then whether this is correct or not, let us check. So this is 0, and here 2 to the power minus 1 into 1 plus this is 0 into 2 to the power minus 2 plus 2 to the power, this is 1 into 2 to the power minus 3. So now this is 1 divided by 2 into 1 plus 0 plus 1 divided by 2 to the power 3. Okay, this is nothing but this is 0.5 and this is equal to 0. This is plus 0.125. So then this is equivalent of 0.625 base 10 value. So here once we are going to get this value, then we are going to note down like this. So 57.625 is of the hexadecimal, this is sorry decimal value 10 is equal to 111,001.101. Then our intention is to convert it into octal. From here, okay, we are going to make the decimal point here. So then we are going to make a group of 3 numbers. So for the octal here 1 2 3 and 1 2 3. So we are going to make like this 2 groups. So this 001 is 1 and this is equal to 7 and this in octal value 101. 101 is nothing but this is 2 to the power 0, 2 to the power 1 and 2 to the power 2, that is 401, that is 4 plus 1, this is equal to 5. So the number what is that? That is octal number, that is 71.5 base 8 is equivalent of 57.625 base 10. Then the last one, instead of doing 111,001.0, that is 101, if you are going to make add here 10 and 1 2 3 4 and 2 zeros, if you are going to add, then you can convert this into a hexadecimal number. So 8421. So then 8 plus 2 is equal to 10 and then this is once again 8 plus 1. 8 plus 1 is 9 and this is 3. So this 3, 9 and 10 is nothing but A is equivalent in decimal. So 57.625 with base 10 can be rewritten as 39.A with base 16 in hexadecimal. With this we conclude this session and next we are going to discuss the logic gates in the next session.